You know, all our modern machines, turbines, robots, you name it, they're constantly talking to us. They're speaking through this massive stream of sensor data, vibration, temperature, torque. The real trick is, how do we turn all that noise into something we can actually use? And that's exactly what we're going to tackle today. So let's jump right in.
Think about it this way. Every single sensor on a piece of equipment is trying to tell you a story about its health and how it's performing. That raw signal is its language. The problem isn't that we don't have enough information, it's that we have way too much of it. The real secret, the key, is learning how to listen the right way.
Okay, so this is where the idea of a feature comes into play. A feature is just a single, meaningful number that we pull out of that complicated raw signal. Think of it like the total energy in a vibration, or maybe how spiky that vibration is. It's one number that gives us a really clear clue about what the machine is doing.
So, here's what we've got on tap. We're going to talk about how to pull key features out of raw data, how to simplify them using something called PCA, and then how to pick the absolute best ones. After that, we'll wrap up by looking at how this stuff is used in the real world and what it all means for the future. All right, first up, feature extraction. This is a super important step. It's where we take that raw squiggly line you get from a sensor and, turn it into a bunch of really useful descriptive numbers. This is where data science really meets mechanical engineering. Okay, so each of these stats, they're telling us a different piece of the puzzle. As you can see, RMS gives you the total energy. Skewness tells you if the vibration is lopsided, but I want you to pay close attention to those last two, kurtosis and crest factor. They are incredibly powerful for spotting faults early on.
So let's really dig into kurtosis for a second. Imagine a perfectly healthy machine. Its vibration signal is usually pretty smooth, kind of like a bell curve. But what happens when a tiny crack starts to form? Well, you get these sharp, repetitive little impacts. And kurtosis, that's just a fancy math term we use to measure exactly how peaky or spiky that signal is getting. And this is what makes it so powerful. The overall vibration energy, the RMS, might look totally normal at first, but the kurtosis value, it'll start spiking. That is our early warning sign that something's wrong.
Now, that was the time domain, but we can also look at signals in the frequency domain. This lets us do things like pinpoint the exact rotation speed of a shaft, or, and this is a big one, we can look at these things called sidebands around a main frequency peak. If you see those, that's a classic sign of a problem in a gearbox.
Okay, so let's say you've done all that. Now you've got dozens, maybe even hundreds of different features from all your sensors. RMS, kurtosis, spectral energy, you get the idea. So how do you deal with all that? How do you simplify it without throwing away the important stuff? Well, that's where a really cool tool called Principal Component Analysis, or PCA, comes into the picture.
Now, I know this process can look a little intimidating, but the basic idea is actually pretty simple. I like to think of PCA as a way to create super features. It looks at all your original features, figures out how they're related, and then combines them into a brand new, much smaller set of features. We call these principal components.
So here's the deal with PCA. There's a trade-off. The huge plus side is that it shrinks your data down a lot. If you need to run an AI model on a tiny controller right on the machine, you just can't handle hundreds of features. PCA can take those and boil them down to, say, just 5. But, and this is the downside, those 5 new super features don't really mean anything physical to us anymore. You can't just point to one and say, oh, that's vibration energy.
All right, so whether you decide to use PCA or not, you're still left with a really important question. Out of all the features you have, which ones are actually the most useful? Out of dozens of options, how do you find the handful that truly matter? And that brings us to the art and science of feature selection. And believe me, this isn't just some academic thing. Getting this right has massive real-world benefits. It makes your AI models way simpler and faster. It usually improves your accuracy because you're getting rid of all the noise. Heck, it can even help you realize you don't need certain sensors, which saves money. And maybe most importantly, especially for us engineers, it makes the whole thing easier to understand and, actually trust.
So how do we do it? Well, there are basically 2 main ways to go about it. First, you've got ranking methods. These are fast and simple. They just score each feature one by one based on how well it predicts a fault. Then you just pick the ones with the highest scores. Then you have wrapper methods. These are a bit more clever. They actually test out different combinations of features to see which group works best as a team, which is usually more accurate, but takes more computer power.
So here's what that might look like in the real world. You could start with, I don't know, 50 different vibration features. But after you do your feature selection, you might discover that, hey, all you really need is a specific combo of just 3 of them to perfectly detect that gearbox fault. It's all about working smarter, not harder.
Okay, so we've talked about how to extract features and how to select the best ones. Now for the fun part, let's see how this stuff actually gets used out there, on the factory floor. Predictive maintenance is, without a doubt, the killer app for all of this. By pulling out features like RMS and kurtosis from a bearing's vibration, and then choosing them as our main health indicators, we can build AI models that are just incredible. They don't just tell you when a bearing has failed. They can tell you it's about to fail, sometimes weeks before it happens. And it's the exact same idea in advanced manufacturing. On a CNC machine, you can monitor features from the spindle vibration and cutting forces. By picking the right ones, like the variance in the cutting force, we can spot when a tool is getting dull in real time. Think about that. You can prevent bad parts from ever being made, which saves a ton of money.
Really, these applications are just popping up everywhere. We're using these exact same principles for all sorts of things. Monitoring the health of bridges and airplanes, getting super precise control in robots by simplifying all their torque data, and even in EVs, predicting faults in the powertrain just by looking at the motor current.
Okay, let's take a step back and pull all this together. What's the big picture here? At the end of the day, it's all about one thing: building smarter, more reliable, and way more efficient machines that are driven by data.
When you boil it all down, this whole workflow is really a 2-step dance. First, there's extraction. That's our translation step. We're turning those raw signals into numbers that show us what's really going on inside the machine. And second, there's selection. This is the focusing step. We're zeroing in on the few features that really matter, which makes everything we do next faster and more accurate.
So, if you remember one thing, let it be this: these techniques are the bridge. They're the essential link between the physical world of mechanical engineering, gears and bearings, and the digital world of artificial intelligence. This is how we give machines a voice that our algorithms can actually understand. So I'll leave you with this question to think about. We're living in a time where literally every single part of a machine can be a source of data. The challenge isn't getting the data anymore, it's about understanding its language. So how are you going to use that language to design, to maintain, and to build the smart machines of the future?